Hello everyone. In the last two classes, we have looked into dynamics of single degree of freedom system under free and forced vibrations, especially seismic vibrations. We have understood the concept of response spectrum, how are they constructed, and we have learned the concept of response spectrum, how are response spectra constructed, and how do we arrive at a design response spectrum. With this understanding of dynamics of single degree of freedom systems, we will move to estimation. We will move to design seismic hazard estimation. In this class, we will look into design earthquake hazard estimation or the design seismic force calculation. In the design seismic load calculation, the first step would be to estimate the design lateral force on any given building. We will distribute the design lateral force over the building height, and later we will also distribute these floor forces among various lateral load resisting members on the same floor. For this, we will look into various methods typically belonging to two different classes, that is static method and dynamic method. In this course, we will be looking into equivalent static method as part of our static method, and within the dynamic methods we will look into two different methods, that are response spectrum method and response history method. In today's class, we will look into equivalent static method. So, the equivalent static method, as the name suggests, it is the simplest method for design seismic load calculation, and therefore it is applicable to buildings which have first translational mode of oscillation having mass participation of more than 80%. If you have undergone course on structural dynamics earlier, or if you have some background, you might be able to appreciate that this corresponds to most of the regular structures. And we have looked about structural irregularities in our previous week, where we have seen different types of mass and where we have seen different types of plan and elevation irregularities. So, this method is suited only for regular structures. The first step in this will be to determine the total design lateral force for the building. This will be based on code estimated natural period of the building. Then we shall move to vertical distribution of the total design lateral force across different floor levels. This will be again based on simple code based formulae, which is appropriate only for regular buildings. And after obtaining the design lateral force at different floor levels, we will distribute those floor forces among different lateral load resisting elements based on floor diaphragm action. So, let us look these steps one by one. The first step to determine the total design lateral force for the building. As we are aware that earthquakes are manifested in form of ground motions or ground shaking. So, usually we consider three components of ground motion. So, we will have the design earthquake force along three directions. In the Cartesian coordinate system, we will have the design earthquake force along two horizontal directions and one vertical direction. So, the design earthquake horizontal force VBDH shall be given by AHD times of W, where AHD is the design horizontal acceleration coefficient and W is the seismic weight of the building. We will look into the seismic weight of the building further in this class, and it is given by sum of all the dead loads on the building and an appropriate amount of imposed load. This is given in table 5 of IS 1893 part 5 2025. Now, this AHD will be given by Z times of I times of ANH divided by R. Here we have a lot of factors, where Z is our earthquake zone factor and it depends on the site location and the design return period, which is considered in our seismic design. It is given in table 3 of IS 1893 part 1 2025. I is the importance factor which depends on category of building, whether the building is normal, important or critical or special. The information about importance factor is further available in table 6 of the code IS 1893 part 5. R is the elastic force reduction factor. We have seen how we have two options. One is to design the building for elastic response and another to design the building for inelastic response, where our design load is significantly reduced. By what factor? That factor is the elastic force reduction factor. We will look about all of these factors in today's class. And the elastic force reduction factor depends on structural systems which is used in the building, whether the building is comprising of OMRF or SMRF, etc. We will look what is an OMRF and what is an SMRF as we move further. ANH, which is again a function of TH, is the normalized horizontal spectral acceleration, and it depends on natural period and damping of the building as well as the site class. We will look how to estimate all of these factors as we proceed. At the same time, the design earthquake vertical force VBD shall be given by AVD multiplied with W. Here AVD, which is the design vertical acceleration coefficient, is given by a product of ZI and ANV. ANV is the normalized vertical spectral acceleration, which depends on the natural period for translation along the vertical direction, damping in the system as well as the site class. Here you should notice that for finding the design earthquake vertical force, we do not use a factor R, that is the elastic force reduction factor. Why? Because we do not expect the building to behave in an inelastic manner in the vertical direction. Now, this point onwards, we will not be interested in design earthquake vertical force for this course. However, when you have to design a real structure, there you might be looking into how do you estimate the design earthquake vertical force. It is not difficult to find. You already have the expression, which is and the estimation is very similar to the design earthquake horizontal force. So, we will be looking into the design earthquake horizontal force in greater detail now. Again, the minimum value of this VVDH, that is the design earthquake horizontal force, is taken as 0.625 times of Z times of I divided by R, everything multiplied with the seismic weight. It represents that the value of ANH cannot be less than 0.625. Also, the final value of the design earthquake horizontal force cannot be less than 1.5% of the seismic weight. To give you an idea, the initial building codes or the seismic codes across the globe started with an approximation of design seismic load as 10% of the seismic weight. Today, this code tells the minimum value of design earthquake horizontal force as 1.5 times 1.5% of the seismic weight. Now, let us look into these factors one by one. Let us look into seismic weight of the building, which is given by the sum of full dead load and an appropriate amount of imposed load. At this point, we should be very clear that the weight of columns and walls have to be appropriately apportioned to floors above and below. The roof live load may be ignored. Okay, let us look into the seismic weight of building, which is given by the sum of all dead loads and an appropriate amount of imposed load. What is the appropriate amount of imposed load? If your design imposed load is up to and including 3 kilonewton per meter square, you need to consider 25% of your imposed load in estimation of seismic weight of building. If your design imposed load exceeds 3 kilonewton per meter square, then in that case 50% of the imposed load have to be considered while estimating the seismic weight of the building. While estimating the seismic weight of the building, the weight of columns and walls have to be appropriately apportioned to floors above and below it. The roof live load may be ignored. Okay, more details are available. Okay, now let us look into the earthquake zone factor, which is given by Z. Our country is divided into 5 seismic zones: zone 2, zone 3, zone 4, zone 5 and zone 6 based on the seismicity of the region. Zone 6 represents the region with highest seismicity. So that is how it represents most of the Himalayan regions. So based on the location of the construction and the design return period of the earthquake, which is considered in the seismic design, we will have the value of earthquake zone factor. These values are shown over here and are adapted from table 3 of IS 1893 part 1 2025 version. So here you shall be able to see that this is based on design return period. We have looked into okay, so the earthquake zone factor depends on design return period as well. So if you have a building which is critical and it's supposed to be operational even in the aftermath of an earthquake, let's say there is a hospital building, we need to have it functional even after the earthquake to treat people who are injured. So in that case the design return period will be larger and therefore it shall be having a larger value of earthquake zone factor. At the same time, you also notice that the zone factor Z is higher for earthquake zone 6 and it is the lowest for earthquake zone 2. Let us now look into importance factor. The current code assigns importance factor of 1 to every building. Now this is not very intuitive based on the functionality of the building. However, we have to understand that the functionality and utility of the building is already considered into the design return period and thereby it is considered in the earthquake zone factor. So we hope that the further versions of the code will get rid of the importance factor I, and the importance of the building is already described in the earthquake zone factor itself. Let us look into the elastic force reduction factor, where the code assigns different values of elastic force reduction factors for different structural systems, such as ordinary moment resting frames will have elastic force reduction factor of 3, special moment resting frames will have elastic force reduction of 5, and henceforth. At this point it should be clear that the structural systems which are better equipped for seismic performance, they are going to have a larger value of elastic force reduction factor. Why? Because elastic force reduction factor represents the factor by which you can reduce the design seismic force due to the inelastic behavior of the structure. There are other factors such as redundancy and over strength as well, but it is mostly because of the ductility but the ductility forms the central component of the elastic force reduction factor. Okay, so this slide contains the values of elastic force reduction factors for different steel buildings and masonry buildings as it was shown for reinforced concrete building in the previous slide, and all of these values are adapted from table 7 of the code IS 1893 part 5 2025 version. Now let us look into the quantity ANH, that is the normalized horizontal spectral acceleration. It depends on natural period and damping of the structure as well as the site class. So the code gives expressions for approximate fundamental translational natural period which is to be used to obtain the value of ANH. There are expressions available for reinforced concrete, steel and other buildings. Further on, the sites are classified into 5 classes A, B, C, D and E based on weighted average shear wave velocity of the soil, which is determined up to the depth of influence. Again, the depth of influence is further defined in the code IS 1893 part 1. So, you must look into the code. So, therefore, I suggest you to always have a copy of the code available at your desk, so that you can refer whenever you need it. In some cases, we will not have the value of soil shear wave velocity known to us. In that case, if you have the SPT data available to you, you can estimate what would be the site class. The code specifies those classifications as well. Once we have the natural period, damping and the site class known to us, we are ready to find the value of normalized horizontal spectral acceleration ANH. Here we have the expression which is given by the code for ANH when our structure or building has a 5% viscous damping. Okay, the figure on the right hand side also shows the same, that is, these are plots for normalized horizontal spectral acceleration ANH for different site classes. As you might have observed that the site class A and B have the same value of normalized horizontal spectra, which is given by this green color plot. We also have plots for site classes C and D, but the plot is not available for site class E. In site class E, you need to first go for soil improvement or ground improvement techniques before we perform the seismic design of the buildings. Now, if your building has damping value which is anything other than 5%, the code gives you provision to multiply the ANH for 5% with a multiplying factor delta, which depends on the damping ratio of the system. This is applicable for viscous damping up to 30%. The expressions are available in the code in the specified clauses. We have mentioned the clause over here, so that you can go to the code and have a look at these expressions. Once we have all these factors known to us, we shall be able to calculate the value of design seismic load in the horizontal direction. Once we have the design seismic load in the horizontal direction, we shall distribute it at different floor levels. The expression for distributing the design lateral force at various floors is provided in the code in the clause 8.2.4.5 and is also shown in this slide. The value of design lateral force at any floor is given by WH square divided by the sum of WH square and multiplied with the total design seismic load in the horizontal direction, that is VBDH. It will be more clear when we will implement these expressions in a worked out example problem in the upcoming class. Once we have the design lateral force at different floor levels, then we can find the story shear. How we will be able to find the story shear? For a given story, the story shear will be given by the sum of all the design lateral force applied at any of the floors above the story concerned. So, if you are finding the story shear in the ground story, you shall be adding all the design lateral forces, and the sum of all the design lateral force will again be given by the total design seismic load, as you might be able to intuitively tell now. Okay, once we have the design lateral force at various floor levels, it is time to distribute that force. Okay, once Once we have the story shear known to us, it is time to distribute this story shear as forces among various lateral load resisting elements. What are the different lateral load resisting elements? They are mostly columns and shear walls in case of reinforced concrete buildings. They are mostly columns and shear walls. So, if the slab is able to provide a rigid diaphragm action, the lateral load, the design shear force is distributed among various lateral load resisting elements in proportion to the stiffness of these elements. But if the slab is not able to provide a rigid diaphragm action, the same will be distributed in proportion to mass of the tributary areas, or you can use analytical model which considers the flexibility of the diaphragm. Now, what is a rigid diaphragm action? If the displacement in the lateral direction of the slab at different locations remain nearly the same, it will be termed as rigid diaphragm action. More details about rigid diaphragm action has been discussed in the lecture on irregularities in buildings, and if the slab is not able to have similar deformations at different locations, it will be termed as flexible diaphragm. Usually slabs with openings are assumed to have flexible diaphragm action. So, we have been able to, in today's class we have learnt how to estimate the total design seismic load on a building using equivalent static method, how to distribute it across different floor levels, and further how to distribute the story shear among different lateral load resisting elements. In the upcoming class, we will illustrate it through a worked out example. Thank you.